Last video we talked about xt graph, and today we're going to explore the vt graph, or velocity versus time graph. Imagine vt graph is a speedometer with direction. It tells you the speed of the object as well as which way it goes in a specific time interval. You can see v, which stands for velocity, on the y-axis, and t, which stands for time, on the x-axis. Now, we can see a black car down there. It starts from rest, because when t equals to 0, the car has a speed of 0 meters per second. But as time increased by 1 second, the speed would increase by 1 meters per second, and so on. So we can plot the velocity of the black car on the graph. And we can connect data point to get a line. Okay, what's so special about the y-intercept of the graph? We know that y-intercept is just when t equals to 0, so it represents the velocity when t is 0. Or we can just say it's the initial velocity of the car. The initial velocity of the car could just be any number. It doesn't have to be 0. Take this blue car for an example. It's moving to the left, that's why it has negative velocity. It's very important to know that in physics, negative does not mean it's small. Getting more negative merely means things are changing in another direction. So let's plot the blue car on the graph. And we connect the point to get a line. You might see y data point here. So what does that mean? You can just think of it as the velocity for each data point. Take this black line, for example. You can see the data point is getting further from the x-axis. And from the scenario, we know that the black car is speeding up. So we can conclude that when you see the y data point is getting further from the x-axis in velocity versus time graph, you know the object is speeding up. It's the same for the blue line here, because when the y data point, when the t increases, the y data point gets further from the x-axis. So we know that the blue car is also speeding up. What about when y data point is getting closer to the x-axis? Here, imagine a car, initially it has a velocity of 3 meters per second. And after 1 second, it has a velocity of 2 meters per second, and so on. Now we have the data point. Now we have the y data point that's getting closer to the x-axis. So we know if the data point is getting closer to the x-axis in velocity versus time graph, we know the object is slowing down. You might already figure out, since negative is left and positive is right, a data point in the positive quadrant would correspond to a positive velocity. The positive quadrant is this part over here. And we can, since the velocity is positive, we can say if it's a point in the positive quadrant, then the object is moving right. On the other hand, if the data points are in the negative quadrant, which is this part over here, we'll know the velocity is negative, so the object is moving left. Okay, now the slope of the velocity versus time graph is also important to know. We know that slope in general is changing y over changing x, or rise over run. So in this case, the vt graph, it would just be changing v over changing t. Now, if you watch the first video, this is equal to the average acceleration. So what can we conclude about that? The slope of VT graph is acceleration. This is important. As a result, zero slope would mean zero acceleration. And a constant slope would mean constant acceleration. Now, what does a zero slope mean? You can see the red car over here. Regardless of the time change, the velocity of the red car is always 2 meters per second. So if we are to plot the red car on the VT graph, it would look like this. It's a horizontal line with no slope. And for constant slope, the blue line and the black line, also the orange line will be a good example. You might ask, what about an increasing slope or a decreasing slope? Well, these would indicate that acceleration would change. Since AP Physics 1 is algebra based, you don't have to use integrals and the derivative to calculate the motion when acceleration is changing. So it's good to know the correlation, but you don't have to worry too much about a curvy line on the VT graph. Lastly, we need to know what the area under the VT graph represents. We know that on the VT graph, the area is just V times T. So we can write the area is V times T. And if you watch the first video, you would know that V is equal to changing X over changing time. So we can actually substitute it in here. So the area would equal to changing X over changing T times T. Well, both changing T and T, they're just representing the time interval. So if we cancel them out, the area under the VT graph would just be changing X or displacement. Since displacement is a changing position, and we know X is position. So we can write it here. By the way, for take this black line as an example. If you're looking at the area, it would be this part. And if it's a line in the negative quadrant, like this blue line, someone would do a weird thing like this, but it's actually not correct. The area is between the line and the horizontal axis. So it's actually this part. Okay, so now you already know all the basics for VT graph. Let's get into a more confusing scenario. Here we have a car. Originally, it's moving to the right with a velocity of 2 meters per second, right? So we know the initial velocity. We can plot them as a y-intercept. And as time increases, the velocity actually decreases. At 1 second, it's 1 meters per second. And at 2 seconds, is 0 meters per second. So basically, at 2 seconds, the car just stopped at that moment. And we can see here, for 3 seconds and 4 seconds, the car actually changed its direction. So whenever a car changed direction in a VT graph, what I like to do is I would separate it into two parts. right? So at 3 seconds, it's -1 meters per second, and at 4 seconds, it's -2 meters per second. We can connect the data point to get a line. Here. So sometimes on the test, the graph here is not given, and you just have to look at the graph, the VT graph. It might be confusing to understand it first because it just seems like a downward sloping line. But remember that the upward sloping or downward sloping line on the VT graph does not matter because it doesn't indicate anything. So do not say that because the curve is downward sloping, the velocity is decreasing. There's no correlation. Instead, we can see here the y data point. It's getting closer to x axis. So what does that tell us? The car is slowing down, right? And since this is a positive quadrant, we know for sure the car is moving to the right. What about this part? We can see the y data point. Although it's getting more negative, it's getting further away from the x-axis. So we know that the car is speeding up. And since it's a negative quadrant, we would know that the car is moving to the left. Okay, hopefully from this example, you know how to use this knowledge when you see a VT graph. I would say the y data point and the quadrant is pretty important, and sometimes it could be confusing when you understand VT graph intuitively. But just remember to understand the y data point and the quadrant. These would be helpful. And to check your understanding, I have a multiple choice question here. You can write the answer in the comment section, and if you have any question, you can also ask in the comment section. Okay, so we're done. See you next time.